Assalamualaikum Ladies and also everyone. Let's move forward to experiment 5. Frictional force. Before we start, let us introduce ourselves. My name is Anis Nazurah binti Abdul Razak.
Hello, my name is Nur Alia Bashira.
Assalamualaikum, my name is Tini Syaira binti Syamsuri.
The objective in the experiment 5 is to determine the coefficient of static friction of different surfaces. So this is the apparatus that we need in this experiment. The first one is wooden block. Second is 50 gram masses. The third one is 10 Newton spring scale. And the last one is string and tabletop. So this is the apparatus setup.
So the first one is the mass of wooden block is measured, record as M. Second one is the apparatus was set up as shown in figure 5.2. The third, the table was made sure stable and horizontally to the ground. For the spring scale and the wooden block is attached with a string horizontally, place them on the tabletop. The rubber side of the block was make sure is face downward. 5 mass of 50 gram mass is placed on the wooden block. 6. The spring is pushed slowly. The block started to move once. The spring scale's reading is recorded. The value is recorded as Fx and tabulated in table 5.1. 7. Step 4 to 5 for 3 trials are repeated. 8. Another 50 gram masses are added on the wooden block, and step 5 to 6 is repeated. The steps are repeated until total of mass is 5 gram is on the wooden block. And now for the experiment 5 result. These are result that we obtained. So the mass of the wooden block with rubber surface is M equal to 81.39 with uncertainty of 0.01 gram. This is table 5.1, rubber surface towards the floor. So the mass is 50 to 500. So the total mass is M plus the total mass is M plus the capital M plus small m. The uncertainty is 0.01 gram. So the first one is 131.39, 181.39, 231.39, 281.39, 331.39, 381.39, 431.39, 481.39, 531.39, 581.39. So the total weight is W with uncertainty of 0.1 Newton. So the first one is for the first one until the last is 1288.94, 1779.44, 2269.94, 2760.44, 3250.94, 3741.44, 4231.94, 4722.44, 5212.94, 5703.44. So these are the static friction force Fs with uncertainty of 0.2 Newton. So trial 1, the first one till the last one is 1818, 4.0, 4.6, 5.4, 6.2, 6.4, 7.0, 7.2, 7.6, and last is 8.2. The second trial is 2.2, 3.0, 4.0, 5.0, 5.4, 5.8, 9, 6.4, 7.2, 7.2, 8.2. The third trial is 2.6, 3.0, 4.2, 5.0, 5.6, 5.4, 6.4, 6.8, 7.0, 7.6. So the average total of those trials, the first one until the last, the 2.13, 3.67, 4.27, 5.13, 5.87, 3.60, 7.07, 7.27, 8.07. And for the second result, which is table 5.2, the non-rubber surface towards the floor. So the mass list with uncertainty of 5 with 0.01 gram is 50 to 500, and total mass of all is capital plus small m, capital M plus small m is same as the table 5.1, and also total weight with uncertainty of 0.1 Newton, which is also same as the table 5.1, but the trials are different. The static friction force Fs is also the same. So the trial one, the first trial is 2.0, 2.8, 4.0, 4.2, 4.4, 4.4, 5.8, 6.2, 6.4, 6.4. The second trial is 2.6, 3.4, 4.0, 5.2, 4.8, 5.8, 0.20, 6.2, 6.6, 6.8, 7.4. This third trial, 6, 2.6, 3.0, 3.6, 4.0, 4.2, 5.0, 5.2, 5.4, 6.0, 6.6, and all average is for the first one until the last one is 2.4, 3.06, 3.86, 4.13, 4.46, 5.2, 5.2, 5.06, 5.4, and last one is 6.8.
First, free body diagram of the wooden block for the rubber surface. We have on the right side, we have force. On the left side, we have frictional force. For the upper side, we have normal force, and below the normal force, we have weight force. But for the free body diagram of the wooden block for the non-rubber surface, we have on the right side we have force, on the upper side we have normal force, and below the normal force we have weight force. The plot graph shows a static friction force against normal force. It can be observed that the graph is a line graph with normal force on the x-axis and static friction force on the y-axis. The linear pattern shows that the static friction force is directly proportional to the normal force. The gradient indicates the coefficient of friction, the coefficient of static friction. After we plot the graph, we have to find the central point of the graph. Thus, the central point of the graph that we have calculated is 3496.19 and 5.58. Then after we find the then we can find the maximum line, best fit line, and minimum line. Next, this is a plot graph of static friction force against normal force on the non-rubber surface. It can be observed that from the graph it shows a line graph with
normal force on the x-axis and static friction force on the y-axis. The line pattern, the linear pattern, shows that the static friction force is directly proportional to the normal force. Then the gradient of the graph indicates the coefficient of static friction. Then after we plot the graph, we have to find the centroid point of the graph. Thus, the central point of the graph that we have calculated is 3496.19, and for the y-axis is 4.757. Then, after we find the central point of the graph, we can find the maximum line, the minimum line, and the best fit line. Now we can determine the gradient obtained from the graph. As I mentioned earlier, that the gradient indicates the coefficient of static friction. So from the kinetic friction equations, Fk is equals to mu n. Compare it with the equation of linear motion, which is y equals to mx plus c. Now we have to find the gradient of best fit line. We have to find the maximum point and minimum point of best fit line. So for maximum point of best fit line, we got 52.5 times 10 to the power of negative 2 and 8.3. For minimum point, we have 6.5 times 10 to the power of negative 2 and 1.0. So after we take the value of maximum and minimum point and putting in the formula of gradient, we could find that the gradient of best fit line is 15.870. Now we are going to find the gradient of maximum line. So first we have to find the maximum point and minimum point of the maximum line. The maximum point that we take is 47.5 times 10 to the power of negative 2 and 8.3. And for the minimum point, we take 12.5 times 10 to the power of negative 2 and 0.55. So we take the value of maximum point and minimum point and put it into the gradient formula. Then when we calculate it, we would get that the gradient of maximum line is 22.143. And now we're going to find the gradient of minimum line. So as usual, we have to find the maximum point and minimum point. The maximum point is 55.10 to the power of negative 2 and 7.8, and the minimum point is 5 times 10 to the power of negative 2 and 2.15. So we take the maximum point and minimum point and put the value into the gradient formula. We would get that the minimum gradient is 11.3. After that, we are going to calculate the uncertainty of the gradient. So we are going to use the formula of uncertainty of gradient is equals to 1/2 bracket maximum gradient minus minimum gradient. So when we put the value, we will get that the uncertainty of the gradient is 5.4125. Now we are going to find the gradient for the non-rubber surface. First, we have to find the maximum point and minimum point of the best fit line. So for the maximum point, we get 55 times 10 to the power of negative 2 and 7.6. And for the minimum point, we get 7 times 10 to the power of negative 2 and 1. And putting those values into the gradient formula, we will get that the gradient of best fit line is 13.75. Next, we're going to find the gradient of maximum line. So for the maximum point, we got 50 times 10 to the power of negative 2 and 7.5. And for minimum point, we get 11 times 10 to the power of negative 2 and 0.5. And putting those values into the formula of gradient, we would get that the gradient of maximum is 17.949. Next, we are going to find the gradient of minimum line. So for the maximum point we got is 60 times 10 to the power of negative 2 and 7.4. And for the minimum point, we got 3 times 10 to the power of negative 2 and 1.5. So putting those values into the gradient formula, we will got that the minimum gradient is 10.351. Then we are going to find the uncertainty of the gradient for the non-rubber surface, which is 1/2 bracket gradient of maximum minus gradient of minimum. So putting those values, we will get that the uncertainty of gradient for non-rubber surface is 3.80. Now we are going to compare and discuss the coefficient of static friction from rubber surface and non-rubber surface. The coefficient of static friction for rubber surface was 15.87 plus minus 5.42, while for the non-rubber surface it was 13.75 plus minus 3.80. The rubber surface has a significantly higher friction because it provides greater resistance to start the motion. This is because rubber's rough texture and higher ability to grip against other materials. For the non-rubber surface, it reduces frictional force, resulting in lower value of coefficient of static friction compared to the rubber surface. Thus, the results show that the rubber is more effective in preventing slipping. Now we are going to the question part. So the first question is, how can anti-lock brakes stop a car in a shorter distance than regular brakes? So for anti-lock brakes stop a car in a shorter distance by rapidly pumps the brake many times per second automatically. This helps to modulate the brake pressure to keep the tire rolling and maximizing the friction between the tires and the roads, and also reducing the stopping distance. To compare it with regular brakes, when you brake hard, the wheels can lock up, which means stop spinning. As a result, when the wheels lock, the car begins to skid. The friction between the tires and the road surface decreases. Thus, with less friction, the car slides and takes longer to stop. Next, we move on to the second question. So from the experiment that we have done, which material has the highest coefficient of static friction, and does it agree with our hypothesis, and what do I think determine the coefficient of static friction? So from the experiment that have been done, the material that has the highest coefficient of static friction is rubber materials. Yes, it does agree with the hypothesis because the rougher surface will produce a higher frictional force than smoother one because they have more surface irregularities that resist motion. The coefficient of friction is determined by the materials of the surfaces in contact. This is because different materials have different surface properties that affect how much they grip to each other.
Assalamualaikum, my name is Dini Syaira binti Shamsuri. So in this experiment, we investigate the relationship between the force applied to a spring and the extension it produced. As we gradually increase the loaded mass from 10 grams to 80 grams, the spring's extension also increased. The initial average extension was 5.45 cm. The final average was 26.7 cm, showing a clear consistent increase. This trend supports Hooke's law, which states that the force exerted by a spring is directly proportional to its extension, expressed by the equation F equals to negative kx, where F is the force in newtons, K is the spring constant, and x is the extension in meters. So by plotting the force against the measured extension, we observe a linear relationship. The slope of this graph gives us the spring constant, which remained nearly constant throughout, confirming Hooke's law was valid within our test range. Based on our results, the experiment successfully verified Hooke's law. We observed a direct proportional relationship between the applied force and the extension of the spring, just as predicted by the equation F equals to negative kx. The consistent increase in extension with added mass and the linear graph trend confirmed by the spring obeyed Hooke's law throughout the experiment. Therefore, the aim to test the accuracy of Hooke's law was successfully achieved.
That's all from our presentation. Thank